record button. And yeah, I think folks know you, so you can go ahead and.
We ready?
I think we're ready.
Okay, take one.
All right.
Well, got a little bit smaller turnout this time. It's hard to beat an eclipse. But I wanted to do something people didn't like see on Nova or whatever. Everybody's seen all the shows about stars and something, and I don't just want to repeat what a bunch of other people say. So this time I thought we'd talk about things that change that you can see with the naked eye, stuff that's accessible without instruments, that's simple enough to grasp what's going on, and I could give you an idea of how dynamic the sky really is. So we're going to cover the constantly active bit. We're going to talk about the skim over what the Earth's motion does to what we perceive. We're going to mix in the moon with that and try to get a fuller picture there. Then we're going to talk about meteors, satellites, aurora, and variable stars. These are the most commonly visible dynamic changes that you can see on a human scale with the naked eye. So do you click or do I click?
You can go ahead and click. That should be.
Oh, look at that. Okay, so our focus today is going to be visual. No tools. Binoculars will work just fine, but for a lot of these things, they're a large-scale phenomenon. You don't need to really zoom in. You just lean back in your lawn chair and enjoy things. And it's great. You can do it anywhere. You can see a few stars. Of course, darker is better, because it increases the sky contrast. You can see fainter things. You can see more stars. The number of stars you can see increases vastly as the sky darkness drops, as the sky brightness drops. And this is what you see when you're in a city. You look up, there's 10 stars. You come out here in Hood River, which is a small town. You can probably see 50 standing in the parking lot. And of course, you get out into the hinterlands and the number explodes. It's really a movie in slow motion. There's always something going on. This is a great shot. It's got so much going on. You got the rotation of the Earth, of course, the famous star trails where you just let the shutter open and the Earth turns the stars for us. Well, apparently. They got a satellite right here. I don't know if the red's visible on the camera there, but there's a satellite streak. And then he caught a meteor. And on the horizon, there's an aurora going on. So this was quite an active night. I'm a little jealous about that one. One thing I've noticed in talking to people a lot of times, people don't really think about the fact that stuff is always changing. It just takes a little bit of knowledge about what you can see and the opportunity, taking the time to actually go out and look and open your mind a little, relax, and just start paying attention. You'll see all kinds of stuff. And despite all these things, people tend to think of the sky as static. They go up, they look, they see the 5 stars from the parking lot when they're on the way to the car, and they don't really think about an hour later those stars are going to be in a different place. Next month, they're going to be in a totally different place. It's continually changing. So the most basic thing, of course, is that we have the rotation of the Earth. The spins on its axis. The axis is oriented this way. So when you're looking off either axis, South Pole doesn't have the Big Dipper, of course. We got the North Pole going here. And the stars are, of course, fixed, and we're spinning, and you get this kind of motion. Now, this is a 24-hour cycle, of course. And at any given time of the night, you will see the Big Dipper working itself around counterclockwise like that. Right now, at an average hour of when you go out in the evening before midnight, it's down here. You can't really see the Big Dipper, right about there to there. You get up before dark in the morning now, you'll see it way high. And a wonderful star trail picture. I'm not sure where this was taken, but it's neat with the fog and stuff. And of course, you can calculate roughly how long you had the shutter open for this. These are the easiest kind of pictures to take, by the way. You just point it and leave the shutter open. By how much of an arc this is. It takes 24 hours to make a full circle. That looks like, I don't know, a couple of hours to me tops. The other thing people don't think about is that everybody's familiar with the motion of the sun across the sky. Well, to reiterate one more time, the stars are doing it too. And you can see this easy enough. It always follows the same pattern, just like the sun. Everything rises in the east and sets in the west and moves at the same relative rate that you would see during the day. The way you can measure this, the simplest way, is by using your hand as a reference. Now, of course, this isn't perfect, but it's good enough to have fun with. You put your hand out at arm's length. That's my hand, by the way. I took it last night when I couldn't find a picture I liked. Hands at arm's length typically have about the same scale between everybody, and this is real handy. 15 degrees from the heel to your fingertips. It's roughly 5 degrees across, and a finger is about 1. So you can do all kinds of things. One cool thing is people see the moon rising, they go, wow, it looks huge, and then it gets overhead, and it's like, gee, it doesn't look so big anymore when it's not right on the horizon. So you hold your hand up and cover it with your pinky when it's rising and see how much it covers. A couple hours later, when it's up and looking smaller, do it again, same size. That horizon is creating an optical illusion, and you can prove it with your measurement skills using your hands. It's kind of cool. Sky moves about 15 degrees per hour because it's got to complete the 360 degrees per 24 hours. And we already know that it's this distance, palm of your heel to your palm to your fingertips. And so if you hold it up at night and you pick a star and you have it on an east-west line, that star will move about 1 hand length per hour. Or you can do this from ground reference things, trees, chimneys, rocks, whatever, anything that's not in the sky, and it will do a finger distance in about 4 minutes. In the Disney movie Moana, there's a part in a scene where they're singing about sailing across the ocean or something, and they've got their cool ships out there going across the sea. And there's a quick shot which really impressed me where the captain is making a measurement with his hand this way. He's going from the horizon line on the water, which is perfectly level, up to one of the stars in Orion. And they would do this to measure a course and keep track of changing, just in a rough manner, of course, but better than nothing, very much better than nothing. You can get within a couple 100 miles doing this kind of thing easy, even if you don't know what you're doing. And they had this all figured out. I thought this was a really cool illustration. I was shocked to see it in the movie. In fact, it was extremely accurate. They even have Orion upside down, as seen from the northern hemisphere, because they're in the southern, and everything's literally upside down there in the sky. So I was pretty impressed. So the other thing we have, of course, the Earth spins on its axis and gives us our days. It also goes around the sun. And everybody knows this, but they don't really think through the implications of what that means. At any given time of night, let's just say midnight, that's the simplest case, the Earth is directly pointed where your position is directly opposite the sun, so you're facing outwards. Well, if you think about what that means, every month you're facing outwards at midnight is literally looking a different direction. And so this is what causes the seasonal changes in the stars. There are different constellations visible at different times of year. People will come over in the summer to look through my scopes, and they'll go, oh, I learned Orion. Where's Orion? Where's the Pleiades? Can't see it. That's a winter sky. So we've got all the different directions to point. Okay. This orbital motion around the sun on a micro scale means that at the same time every night, the sky is clocked 1 degree more west. And that's the micro manifestation of that larger motion every month. So when people learned the Big Dipper or whatever was like over that direction, and then we're out and they go, well, where is it? Well, that was last month or in the spring and it's now the fall, and things are constantly moving. So you have to account for the season and the time of day. So when you look up at night, say tonight, and we see the fall stars, the later you stay up because of the Earth's rotation, the winter sky starts rising as well. And so that's why now, if you're getting to work before or getting up before dawn, you'll see Orion smack way up high in the sky. Winter constellation, it's fall, but the sky has advanced 6 hours because of the nighttime rotation thing. This whole deal confuses a lot of people. It makes things very tricky. So here's a little bit more detailed map of the, the orbital motion around the sun. The basic path that the moon and planets follow through the sky. The solar system lies in a single plane. It's a big dish, and the planets and stuff all tend to stay in this. And the apparent path that the planets and the sun and the moon trace against the stars is through the constellations of the zodiac. So this is the only distant connection between the science of astronomy and the pseudoscience of astrology, is they both started out from observing the motions of the planets against the stars. So in May at midnight, when you look outwards, we're facing the constellation of Libra. But if you could see the stars in the daytime, you would see that the sun appears to be in Aries. And that's your sun sign. That is how they give you that birth sign when you're supposed to go look up your horoscope. It's where the sun was during the day when you were born. Now, since the time when they came up with it, the Earth's orbit wobbles. There's a lot of small motions, and so some of the relations have changed. I can't remember which way it is, but now they're off a little bit from the classical designations because things have shifted over the few thousand years. But that's what's going on. Daytime against Aries, nighttime you're looking at Libra, and you just go on around now. Right now, of course, we're looking at right in, is it Pisces? Yeah, I guess it is. That's right, that's what I'm seeing. See, I'm messed up because it's getting darker earlier every night, and at this time of year, the stars appear to stand still if you go out and look when it's dark, because the darkness is getting earlier, right? If you go out at 9, you get the same normal clocking. Dunk, 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 dunk. Everything's farther at 9. But since I'm looking at 9 and then 8 and then 7, I'm looking earlier in the night. And so the sky appears to hang up for a second in the fall. It's pretty interesting. So we got lots of motion. We got the Earth rotating, or we got it revolving around the sun. Then we throw into all this confusion the moon. Now, we talked about this a couple of months ago, so I'm not going to linger too much on what's going on. But the moon's going around the Earth. It takes about 28 days. I think we're all familiar with the phases. You look at how the shadow falls on a ball as you rotate it around with a light next to you. It's always half lit up, but depending on the angle, you see it from different directions. And the shadows change. The other thing is the Earth and the moon are tidally locked, so the day of the moon, its own rotation is exactly the same as its orbital period. So as it goes around, it's turning at just the right rate, so we only see one side. There is a dark side of the moon, but it's constantly changing. It just means which part's in the shadow from the sun. However, there is a fixed far side of the moon that's very real. It's the side that never faces us. And until the early 60s, when the Russians flew a satellite past the moon to look at the other side, nobody had ever seen the far side of the moon, ever, at any time. It was a complete mystery what was back there. The other consequence of the rotation is we go back to that same time of night thing, which is always crucial to give you a fixed reference for some of these motions. Since it's moving counterclockwise, it's shifting a little each day. This spins around once, and the moon goes here. Now it takes the Earth a little bit more of a turn to catch it. So it rises about 50 minutes later each day. You can measure that with your hand. It's a little shy of the heel to fingertip thing, but if you go out tonight and do this with the moon, look tomorrow night at the same time, it'll be on the fingertips. And you will see the phase has shifted a little bit. So I think I covered that here. Go out and look every night. It's working eastward. It's fun to do a little prediction and see that it comes out. You're like, wow, I'm an astronomer. This here is not to scale. The phases aren't quite right. I just threw a couple of GIFs together, but you can see what I'm talking about. It's crescent. It's now a half a moon. It is marching eastward across the sky, and this is continually going on. In fact, the rate the difference of the rate between the moon and the fixed stars in the background, if you're taking pictures of the moon with a telescope, you actually need to set your clock drive to a slightly different rate to account for that drift. Now, it won't screw up your high-speed pictures because, you know, it takes longer than that to show up. But as you're focusing on a particular target in a small area on the moon, you will see the moon drifting even though your clock drive is normally dead on, and that tells you that you haven't set the lunar rate, which accounts for the moon's motion too.
Chris, is the moon's motion retrograde in some sense, or is it just...
Oh my gosh.
Is it rotating around the Earth in the same direction as the planets rotate around?
I think it must be, or else we would hit it earlier every day. We're chasing it. It takes 50 minutes later for it to be in the same part of the sky. It must be the same direction.
Okay.
And I take it because there's always one side of it that's facing outward from the Earth. Those pictures from the Russian satellite might indicate more craters on that side?
It is absolutely true. The other side of the moon has been pounded. It took.
Say that again. What's the reason for that?
The question was, what did the picture show us on the far side of the moon when we finally got to see it, and did it have more craters? And the answer is yes. It was facing outward during what's called the late heavy bombardment, which is the last major shifting of the planet's orbits. That's another thing most people don't realize. The solar system was very unstable when it's in its earliest formation, and Jupiter and Saturn and major planets were actually shifting around, and the gravitational tides of this were throwing rocks every which way, and there was a period of very heavy bombardment where everything was just getting plastered by the disturbances of these planets shifting, and the far side of the moon facing outward caught more than the interface because the ones coming from the inside had a likelihood of hitting the Earth. Right? And so it's very heavily cratered. There are very few of these vast lava plains on the backside. It almost all looks like this area where it just craters, 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 craters. It's a very good question. Okay. Another motion is libration. And the moon's going around the Earth. It's also at an angle. Both bodies have a very minor wobble to them. There are some other motions going on, and what this means is even though the moon faces geometrically 50% towards us, right, of the surface area, it's also shifting ever so slightly on different orbits. And so technically over time, you can see, I think it's 55% of the moon's surface or something, because now and then you get to look slightly around one corner. And this happens at the top and the bottom. This was the simplest one I could show to illustrate. There's actually movies that show you the whole wobble taken over many years. But I couldn't get PowerPoint to play MPEG, so that was that. Meteors. Everybody loves meteors. They're screaming around. They're always pretty to watch. Kids get really excited. So what are they? Well, a lot of them are bits of comets. Comets are dirty snowballs from the early formation of the solar system. It's a ball of gas and ice, and there's rocks and bits of whatever mixed in there. And as they go around the sun and melt, the stuff dislodges, just like those freaking snowdrifts with all the crap plowed into it last winter. In the spring when it melts, they got this dirty snowbank, and it turns into a pile of rocks on the driveway. Same thing. So it's the comets, it's debris that wasn't yet encapsulated into other bodies and is still floating around out there. Plus, large bodies hit other large bodies, a fair amount within the solar system. This was mostly during the formational phase, was most of the violence. But of course, out in orbit not near like the Earth's orbit with the satellites, there's a certain amount of drag from being low that comes from the atmosphere. It's thin, but it's not absent, so it slows things down and they fall down. Out in deep space, there's no friction at all. The tiniest bit of dust can follow the same orbit for 1 billion years. And so when something hits Mars or the moon or the Earth and it spalls pieces off in every direction, those things go flying and a lot of them never come back. There are known and proven pieces of Mars on Earth that were knocked off of Mars by an asteroid impact, flew around for God knows how many years until it wound up on Earth as a meteorite. And this was one of the earliest ways they had of sampling some of the distant bodies before we had spacecraft. They would look at the spectra of the Martian plains and find a meteorite that had just the right spectra when you burned it in a furnace. And they'd go, oh, this looks like it probably could be from Mars. And also the moon, a lot of samples, and some from Vesta and some of the larger asteroids as well. And so people got a lot of mileage out of this once they realized that it was possible. And it makes sense. You know, if pieces are going to break off, they're going to fly around. You'd think, though, that space is so big, how could they fall on Earth? Well, some of them do, eventually. Got a lot of time to work with. The other cool thing is a small fraction, about 2%, may be from outside our system. They are literally interstellar bits from God knows where in the galaxy, other stars, travel time, who knows. They're not moving very fast. So a long, long travel times, and yet a few of them fall on the Earth. And the cool thing is, this means, of course, that when you see a set number of them, maybe 100, 2 of them that you saw were from another star, another system, gosh knows where. Let's see. Meteors are in the sky. Meteorites are what's on Earth. Sort of like the cave things, stalactites, stalagmites. Stalagmites are on the bottom growing up. Stalactites come down from the top because they got to hang on tight. That's how I remember it. Meteors fly through the sky, and then you pick up the meteorites on Earth. They're kind of fun. I should have brought one in. You can buy them. There's a thriving market in them. There's expeditions to find them. They find them in the hardpan areas out in Africa. The Sahara is huge meteorite place. Antarctica, where you've got a nice white background. If there's a rock on top of the snow there, it came from the sky. You can get little chips of meteorites, I don't know, 10, 20 bucks. And it's kind of fun to hold something in your hand that was flying through space. I don't know why it's so cool. We're all flying through space right now, but you know. So this is what's going on out there. There's a network of cameras around the world now that feed into, I can't remember who does the calculations, but they catch them on the all-sky cameras that run all night. They know the coordinates of each station where there's a camera, and so they can tell if they've seen the same one from 2 different angles, and then that allows them to calculate the orbit. And so here's the Earth right here. Sun, guess that would be Mars's orbit, Jupiter, Saturn. And here we have to scale what's going on with some of the sources. You've got these little guys in here that aren't moving that far, and they're going pretty slow. That's the red coding. Here's the speed, kilometers per second. Red is 18 kilometers per second. Blue is nearly 70 kilometers per second at 66. And what you'll notice is the closer ones are the slower ones, and the ones that are going way out with the very straight paths. I mean, look at this thing. That thing has a massive orbit. That's the orbit of Saturn, and it's almost a straight line. That thing was traveling a long, long ways, and it fell a long ways. And so when it's getting in closest to the sun, it's really smoking along and hits us at very high rate of speed. And you'll see this at night when you're out looking. The random ones, the sporadics, they'll have all different speeds. Some will just, you turn to your buddy, and of course nobody usually sees them. But some of them, you'll notice, have some hang time, and it takes them a little bit of travel time, a couple of seconds. Those will be the red guys. So there's a fair amount of variations in speed. Colors occasionally, usually they're white, but the brighter ones can be red, orange. Green is a common color. Yes?
You said a couple slides ago that the pea-sized asteroids have, or meteors have produce the best show in the basketball-sized ones.
Oh, I'm sorry. Was I? Oh, there we go. Yeah. Typically, the ones you see are very, very tiny, grain of sand, piece of dust, whatever. They're moving. They burn up fast. That's just your common one. The one the size of a pea or marble, you'll be like, wow, and everybody will gasp. And when they get up to about this big, it will make it look like daylight for 5 to 10 seconds, and typically they'll leave a trail, and you will see shadows move as it crosses the sky. It's quite impressive. So we did that guy. So,
meteor enters the atmosphere, like how big does it need to be to be the size of the golf ball by the time it gets to?
okay, that's a good question. I should have done more research on that. I didn't. I'm just going to do a little arm waving here. For one thing, it's a combination of variables, including speed and angle. If it's moving slower, a smaller one can get through because it's not as hot when it hits, right? If it's coming down steep, there's not as far to get through the atmosphere than if it's coming at an angle and it has to go through a lot of air before it gets to the ground. So that would require a slightly bigger one. I would guess that all things being equal, you're starting with rocks in this range at that size when they enter to get to the ground, as opposed from something large disintegrating and sending shards. That's you can see how that'd be completely different. For a single body to come from outside the atmosphere, I'm guessing this size-ish to make it to the ground, all things being equal.
Have you ever seen one of the ones that threw shadows?
Yes. Yeah. A couple of times at random, because I've been observing for a long time. And then during the Leonid storm in November, I think it was 2001, saw a lot of them. Yeah, 5 to 10 in one night, easy. Yeah, it was crazy. You know how flash looks at night and everything's all stark white for a second? Well, this is moving through the sky, and everybody in their lawn chairs and stuff is suddenly like daylight, and you can see the shadow doing this past everybody. It's really cool. It's quite amazing. That was quite a storm. So observationally, the meteors are grouped into two different batches. Yeah. Observationally, the meteors are mixed into two different batches. There's the sporadics, which are just those random ones. We saw a bunch on that earlier plot with the orbits. They're coming from wherever. They're not particularly associated with anything. Speed, color, direction, everything changes. And then there's the showers. These are all associated with each other. They're traveling together. They have a common direction. They have a much smaller variation in their range of speeds. They tend to be composed of the same kinds of things, so they look similar. They'll have similar colors. They're almost always shed from a larger body like a comet or an asteroid. As the body orbits the sun, particles pour off of it, and of course, once they leave that body, the momentum they have is fixed now. So the instant they leave that body, they now have their own orbit that they just follow. And so thousands of these, millions, billions of these things are just traveling in this common orbit. And as the object goes around, it's like leaving smoke trail in this big ellipse. And the smoke trail is comprised of all the little pieces, and that's what we're seeing. So for the Perseids, here's sort of what you got going on. You got the main swarm of these bits following the passage of the comet head. Gravity affects everything in the solar system. The longer it's been since the comet has been by, the more other bodies have perturbed the orbits of these little particles and spread them out. Right behind the comet, that hasn't happened yet. And so the bodies associated with it are still densely oriented in a fairly thick cloud. So we go around the sun, the orbit of the comet kind of hangs there, and once a year we intersect it and fly right through the dust cloud. So here's another example. It is literally a cloud of stuff that the Earth is traveling through. In the case of Temple Tuttle for the Perseids, this has been going on for thousands of years, and the multiple passages of the comet plus the effect of gravity in spreading the particles has made a huge area there now. And so the Earth technically goes through it for about 3 weeks. You will see some early Perseids a couple of weeks before that peak, the second week in August every year, second or third, whatever it is. Into the end of July, you'll start seeing, if you know how to measure the directions, you'll see one, oh, that's probably an early Perseid. And then it will pick up to the peak, and you'll see a whole burst that night, and then it will taper off again. But that's why it lasts so long, is the cloud is fairly large compared to the size of the orbit of the Earth.
Peak is what, sometime in August.
It's usually like the 15th to the 19th, somewhere in there. It's the one everybody thinks of as the summer shower. Meteors are very dependent on dark sky conditions, just like everything else. You're going to miss the fainter ones, so everybody prays when there's big showers that the moon's going to be gone for that period. If the full moon's up smack in the middle of the sky, it'll cut you by 2/3. You'll just see the brighter ones.
Chris, that cloud is orbiting too, right?
Oh yeah. Mm-hmm.
So
everything's in constant motion. Some years are better than others. This knot that you see right behind the comet is also moving with it. So sometimes you pass through and you're just getting this part. Other times you hit the knot. It's super dynamic. It's a very new science. They've only been doing it for about 20 years now in terms of modeling the orbits of these things. The Leonids at the end of the 90s and the beginning of the 2000s, its comet Swift, I think it was, had just passed. And they had just developed the mathematics, and they were able to do simulations and then look at the storm in November, and then simulate some more and look at the storm in November, and they got really good at it. So the other impact of all these particles traveling in a common direction is that as seen from any fixed point, they appear to radiate from a specific place in the sky. It's like if you were to somehow carefully stand in the freeway with cars going past you, they would come from on both sides of you and appear to be coming from a common direction. Or like when you look up at the rain, it all appears to be spreading past you. That's all that's going on. There's enough to be distributed around you, and so they appear to come from a particular place. And that's how these meteor showers get their names, is by the place that they appear to radiate from if you're standing on Earth. Perseids come from Perseus. And so you get this all directions thing. Now, what this also means is you stretch it overhead. When they're overhead, they tend to be longer because they're traveling past you on a much longer path. When they're off the direction of the radiate, they're much shorter because they're foreshortened. It may still have even traveled the same distance, but because you weren't under it, like the guy 500 miles west of you, he saw a long one, you saw a short one because it was coming towards you, even though it was the same meteor. That's part of how they track the meteors with the cameras to make those orbital diagrams. So the impact visually is this. So it's a long exposure. You wouldn't see this at night, right? This is probably about an hour, I would guess. An hour's worth of time, but in probably 30-second frames that he repeatedly added, he or she, because you see the stars are not trailed. Kind of looks like going into warp drive or whatever in Star Wars. The interesting thing is that 2001 Leonid shower actually did look much like this. As the eclipse was to looking at the sun and the moon, that meteor storm was freaking amazing. Absolutely amazing. I did an experiment. I closed my eyes, I opened them, and I counted, and I saw 17 meteors in 10 seconds. Doubles, triples, the sky was just constantly alive. Faint ones that would explode. It was just amazing. I think that night we reached a rate, I think it was 1,500 per hour.
Did you know it was going to be like that?
Yeah, the prediction. This is when things were... What's that?
That's the Perseid one?
No, this was the Leonids. It's a November shower. It had this one period of activity that has a comet, I think, on an order of 33-year period, and the comet had just come through, so the stream was very fresh, and they were making all these predictions.
Okay.
Where did you go to see that?
Excuse me?
Where did you go to see that?
It didn't matter so much other than in a large geographical area, like Japan was pointed the wrong way, that kind of thing. We just got out of Seattle and drove to the eastern side of the mountains towards Ellenburg to get some dark skies. Mm-hmm. That's all it took. Well, the other kind of miserable thing there, the hard thing about the Leonids, is that November, when it's clear, it is freaking cold, period. And so we're talking long johns over sweats, over nylons, 42 layers, and in a sleeping bag, and wrapped in a tarp. With just our heads sticking out. My coffee froze solid.
Do you know if there are any other showers like that upcoming in the next,
Well, everybody wants one like this, and there's none on the horizon.
Not for 33
Well,
years
that's
from
the
last
thing.
time.
That's the period, but you also have all the other motions. The predictions for the next Leonid storm is 2 cycles out, which means 2072 or something. I don't think I'm going to make that one.
Is that your shot?
No. These are all stolen off the interwebs. But here's what the Perseids look like from our orbital friends. You can definitely see the trend there. And so you can see there is a place here where they're relatively concentrated and the distribution is higher. Those are the newer trails of the particles. And then the spread here is usually the older particles that have been perturbed as they pass by the planets in their slow orbit in the smoke ring. Now, there's also some observational bias here because, of course, we're measuring them from the Earth. And so the only ones we're seeing have this foci. And so it's concentrating things maybe a little more dramatically than it should, but it's still a valid representation. And it's really spectacular to see how correlated they are with that stream. And you saw the other two were kind of random, and this is like, boom, tons and tons and tons of them. So the Perseids on a given year will rank anywhere from 60 to about 120 per hour. So that's 1 to 2 per minute. It can be real bursty. You'll see a bunch of them and then wait 10 minutes and see nothing, and then a bunch more with a few spread out through. It's a very interesting game, but the Perseids usually deliver, and of course people love it because it's actually warm out. Oh, the other thing about meteor showers is usually they're the best after midnight. That's what people hate the worst, but this is science. Nobody said it was easy. At midnight, you're facing forward in the direction of the Earth's orbit, and so you're collecting more stuff. You see more meteors. Before midnight, we're facing somewhat backwards in our orbital direction, and the meteors that you see have to catch the Earth, and it's a little tougher. So the rates always increase after midnight, even the sporadic rates. This is the guy associated with the Leonids, and I put this in, number one, to show how far out some of the particles go. Way the heck out there. This is like 1.8 billion miles. I think that's right. The other thing I liked about this one is it showed you the two paths. I kept saying the comet leaves trails and trails and trails as it go. Here you can see that the perturbation by orbiting past other things has shifted the orbit a little bit, and that's what scatters the particles in the meteor streams. So here's a time profile of I guess it was 2003 I saw that. So this is the hour, this is the rate, and so zenith hourly rate, we hit 120 here. This isn't the storm though, I got this wrong. This was a good year, but it wasn't the big one. I think the big one was 2003. But this was good, 120, that's as good as the Perseids. And then 60, that's still as good as the Perseids.
Yeah, they're all during the day.
What's that?
They're all during the day.
This is UT.
Oh.
Aha. Good catch, though. And as you can see, it's spread across a few 6 hours there. And here's the interesting thing that these numbers mean. This isn't the rate. That is the year. That is the orbit left by the comet that year of its passage next to Earth. Because remember, these smoke rings orbit forever. And so when the comet came into the solar system and went by the Earth in 1733, it left a smoke ring. That smoke ring's still there. Another time, 200 years earlier, it came through in 1533. That smoke ring is still there too. And so we hit both of them. A 400-year-old trail and a 200-year-old trail. The other cool thing about the Leonids is that they tend to be rich in bright meteors because the stuff is relatively fresh and the chunks are big. And you may not see a high rate. Technically, even in crappy years, you're more likely to see bright ones, which is fun. The Perseids are kind of a relatively flatter aspect. They're medium to bright, and there's a fair number of them with not a lot of faint ones. This guy is definitely weighted toward the very, very bright ones. How many can you see on average? Well, the weird thing is there's a cyclical pattern to the sporadic background rate. It's not just 4 to 6 or whatever per hour. That's the average overall, but it's the lousiest in May and June, and the best when it's freaking cold out. Figures, huh? I'm not sure. I didn't do any reading. I suspect that the high November numbers are a result of the background of faint Leonids associated with that Comet Temple Tuttle. It's so potent sometimes that I think that's what's biasing the results here, although it doesn't explain why it's big here. I don't know. You get your bonus for brave in the cold, though. You get to see more in the winter if you can stand it. At any given time, there are a ton of showers going on. There are a lot of meteors and comets. There's always something going on. This is from a great place, Comets and Meteors Online, Meteor Showers Online. So really what you're going to see is the contribution from the average background rate at any given time plus shower activity. We're lucky this month we got a good one, the Orionids. This is pieces of Halley's Comet. And it has a pretty good rate, 50 to 70, around 1 a minute on a moonless night. So that's going to be kind of satisfying. The weather at that October 21 can be pretty dicey, but I'm not sure what we can do about that. And then all these faint guys. So this is 50 to 70 per hour. These recommended expert experience, these can be from like 2 to 10 per hour tops. And so they're mixed in with the background rate of random ones. And so you really have to be paying attention to pick up on some of these guys. And again, the weird names come from the constellations that they appear to radiate from. The Orionids appear to come from Orion. And there's a daylight shower, the Sextantids, in the southern hemisphere constellation. And those you can only see with radar. This is what I went over to Space Weather and grabbed this one for yesterday. This is what was seen yesterday. 30 sporadics, 2 southern Taurids, and 1 daytime sextantid, the one we just looked at here. So the camera caught one of these guys. I don't see any Taurids on the list. That must be for September. But so it's always happening, and they did catch some shower activity with their cameras. That's what they look like from space. It's pretty cool, huh? Floating up above it, stuff's burning up beneath you. That must be a little bit freaky knowing it's passing you by. Satellites. Oh, geez, I got to get going. There's 1,000 satellites in Earth orbit in 2013. Half of them launched by the U.S., half of them below 200 kilometers. Know if you remember the scene in Wall-E where he escapes the Earth, hitches a ride on a spaceship, and he's bumping through all the space junk? It's not far from true. There's so much stuff up there. That's the Clark Belt geosynchronous satellites, 23,000 miles up, 22,000, whatever it is. And then everybody else's stuff doing whatever. Some of these things are parking orbits for old dead satellites. They don't have enough propellant to get them down, but they'll push them out so they're out of the way. Because once you run out of propellant, you can't steer it anymore. So you got to plan what to do with it. Typically, any dark place, you'll see 5 to 10 in a couple hours, all brightness ranges. The space station is crazy bright because it's huge and low. It's the 3rd brightest thing in the sky now. Sun, moon, space station, even brighter than Venus. It isn't always that bright. It depends on the past, but it can be. And when it is, it's freaking amazing. It's like you know what an airplane looks like when that spotlight's looking at you, except it's not changing. It's just going straight overhead. Nothing's blinking. It's just crazy bright. The fast movers are low Earth orbit. Has to move faster to stay up. Most naked eye ones are very much north to southish and not so much across the sky, east to west. I often see this pair. Every few weeks I'll see this pair. I don't know what's up with that. I think there's some gravity experiment or something, but there's two, and they just stay locked in position relative to each other. I should read up on what they're doing.
The app doesn't tell you?
I don't have an app. That one app might.
There's Space Walk, what is it?
Oh, skies above?
Let's see,
We used Orbitron in the past. You know that program you can download, and I think it'll show you what satellites are where. We used it to we were testing out the Iridium.
Oh, good
modems,
idea.
You know, to see like
To
when
tell-
the Iridium satellites.
Oh, that's a
were
good
by.
idea. I'll have to look into that.
Yeah, I have Starwalk.
So there's so many damn that you see them all night long by eye, and then even in my scope with a tiny field of view, I'll see them every night, often multiple times, through a half-degree field of view. Something will go trundling through. There's a lot of stuff in space now. Oh, and they change brightness a lot. They'll fade when they go into the sunset up high. They'll get bright out of nowhere, coming into the sun from up high. They tumble. You'll catch a glint off of a corner. It can look like something exploding. It's very disoriented. You like see this flash. You're like, geez, am I stroking out? No. You're taking pictures with your telescope, and you've got your nice 2-minute frame that was perfect, except somebody went trundling through the picture. Very annoying. That's not my shot either. The geosynchronous belt is pretty cool because, of course, they hang in place. They don't move. So you do a star trail. You look for the dots. Those are the geosynchronous satellites. They're fixed with you in the trees and the buildings because they're geosynchronous. They don't move. So you can take a star trail toward the equator, look for the points that aren't smears, and you've got geosync satellites. Ooh, Aurora. Everybody loves this one. This is a cool one, but very rare here. Not impossible. So what are they? You got the solar wind coming from the sun. It's got a charge, therefore it's affected by anything else with the charge. The Earth's magnetic field is magnetic. Charged things are moved in magnetic fields. And so the stuff from the sun hits the Earth, goes swooling around, gets concentrated at the poles. It heats up the upper atmosphere, causes it to fluoresce. So here's a simulation of a coronal mass ejection. This one didn't hit us, but the sun spins, and the solar wind has some tides in it, kind of, not really tides, sort of gusts or something, and you get this spiral pattern. And then here's an explosion boiling off of a big flare on the sun, and you can see it expanding out. So here we are on Earth with our little protective magnetic field, and then this big hot dense thing hits us, and it bends the whole magnetosphere, and this is when the auroras are going on. Boom, right now.
Did you happen to catch the one last week?
No.
That's kind of bad.
Here's their simulations from above the Earth. They still run this particular program. You can look at these at the space weather site and see what's going on. This one was so intense that it knocked some polar satellites out of control. They could not control the attitude of the satellite anymore. Sensors had been damaged. One of the big satellites had hundreds of events from the memory being damaged by charged particles. And it also took down Quebec's power grid, blacked them out. These are huge currents at work. Long cables, like power lines, make great antennas. And so these auroras induced immense voltages across the network and tripped everything.
So how far up north typically would we have to go? Like, I think I saw people in Bellingham saying they could.
Yes, it's not that bad. On a given night, we'll talk about that in a minute. This is typically what you see around here. It's one of the arcs. It's this thing here, seen from way down here. So it's a low arc hanging on the horizon. I saw one in May. But that's the most common thing. And then what will happen is, as it gets powerful, it will move farther and farther south, which means farther over you. And you'll also start to see the streamers and rays. You can kind of see a few streaks here. But it's on the northern horizon. It's hard to see.
Is there a certain app that would be best to...
Go to Space Weather and just look at their maps. They have an ongoing map. It's up right now. It's permanent. So how often can you see them? Well, they cycle with the 11-year sunspot cycle. They do require exceptional conditions. You got eastern horizon. You want no moon, so you got the high contrast. Plus, you have to have whatever it is from the sun hitting the earth and getting everything all energized. Up north, where the pole is, the magnetic field lines of the earth are more concentrated. It's more sensitive up there to less disturbance. So that's why they see stuff in Alaska all the time. It just takes a kiss from the sun, and boom, things will get active. To have it go far south, it's got to be big. When you're out looking, it's always something, man. You got the lights, it's foggy, it's infuriating to look on that app and see an aurora going on and it's raining. That is absolutely infuriating. So any year that's not at the solar minimum, the 11-year sunspot cycle, any year it's outside of that, which is about 9 years, I would guess that from here you could probably see them a handful of times a year, assuming you had perfect conditions all the time. If it was always clear, you were on a lake or a mountaintop, and it was pitch dark, you could probably see something on the horizon several times a year.
Did you just say, so where are we in the sunspot cycle?
We're approaching the minimum right now.
Oh, okay.
That big burst a couple of weeks ago was anomalous. It was quite a good show from what I'm told.
Oh, yeah. I saw some shots from the Oregon coast.
Yeah. Okay. Oh, yeah. And the other thing, if you do travel and you're going to Europe, when you're doing that polar flight, look out the window at night. It is very common to see them out the window. And out the window from space, too. That one's pretty cool. God, that must be amazing to fly over. Those guys. And now they got that big picture window thing installed. Did you know about that? Yeah, they put this big viewing cupola on one end of the ISS. Nothing but windows like a science fiction movie. Okay, last item. Variable stars. Stars change brightness all the time. Most people don't think about this at all or even have a clue about it. We talked about it just a little, though. The sun does. It's got that sunspot cycle. The sunspots are a finite size. You can see them on the surface. They're darker than the rest of the sun. So if you measure closely enough with the sunspot cycle, you'll see the overall brightness vary, because when there's fewer spots, there's more bright. Sun's brighter. When there's more spots, there's more dark. Sun's dimmer. The sun is a variable star. Very, very small luminosity range, because it's never got that many spots, but it has an 11-year cycle. But this is very common through stars. This is second magnitude. That's a fairly bright star in the sky. You can probably see it even in a downtown area. And this is ninth, which requires at least a 2.5-inch telescope to see. And look at this light range. This is hundreds of days. It's swelling and shrinking, swelling and shrinking. There's two types. There's intrinsic variables, where something is unstable inside the star. These are usually due to pulsations of some kind, and the surface area is increasing or decreasing, and the temperature and thus color brightness of the star is increasing and decreasing. And so the intrinsic per area brightness of the star and its temperature plus the size variations can make all sorts of crazy differences. Pardon me. Here we go. Differences in the brightness. They can occur on minute scales. Some are as short as 70 minutes, 8 years, or centuries. And of course, if it's inherent to the star itself, this also includes nova and supernova technically. They're sort of a one-event thing usually, but still, that's a variation. Then there's the extrinsics, and this is where some other mechanical thing is going on that makes the star appear to change brightness. And this is almost always orbital. One star is getting in front of the other in a double star pair, and so it's eclipsing. So you get these pulses, and it's not because of the star changing, it's just them bumping each other. Okay, so I lied a little. Variables are particularly fascinating when you got a scope, because you can see the faint ones. This one I've observed for a while. It spends a lot of 6 is right about naked eye magnitude in the dark sky. And with magnitudes, the bigger a number is, the fainter it is. And 0 is a crazy bright star, and minuses are very bright. The sun is minus 26, the moon is minus 13, space station's about minus 4, Vega at night overhead is 0, and so 6 is faint, 16 is really faint. This star goes perking along, and every so often it generates this huge cloud of carbon within its atmosphere, and it blocks out the light. And this time, it stayed. So it got, holy crap, 10 magnitudes fainter, and stayed that way for, 2,000 days. Then you got this little guy. He's just 87-minute period. Now, it's only a half a magnitude variation, but that thing is going crazy. This guy's my favorite, SS Cygni. It's in this fall-winter sky, or summer-fall, and I watch this one a lot. It sputters along at a basic faint 12. It takes about a 3-inch scope to barely see that guy. And then every so often, boom, it shoots up to 8. 100 times brighter. I've heard that if you're looking on a night where it's transitioning and the event happening and you catch it right here, you can watch it brighten over the course of hours. I would really like to see that. So this one you gotta kind of get into a habit. I'm out every night. I'll go look. What's going on? And for a while, it's so boring. And the girlfriend's, oh, why can't I see anything? This is changing. We always see the same darn thing. And then one night, you look and you can't see it because the stars look different. There's a bright one there that wasn't bright, and it's the one you've been watching, and it's thrown off the pattern. And it takes you a minute to recognize that you're looking the same place. And that formerly thing you could barely see is now so bright. It's very cool. What's going on is there's a dwarf star, which is nearly dead. It's got no fusion left. It's slowly cooling down, but it's very, very hot and intensely bright. And it sucks matter off of its close companion friend. And it's all orbiting in and falling on the star. This disk plus the star is so bright that it actually lights up the surface of its companion star. It's hard to get your head around that. It's like making another light bulb brighter because of a really bright one next to it. That's how much energy pours out. There's a shadow of the disk onto the other star, all sorts of complexities. But the bottom line is here, hydrogen piles up on this guy that's being sucked from that dude, and then it reaches a critical mass, and boom, it all goes at once. And that's that pulse that you see there. It takes about that long. Every 30 to 40 days, enough material transfers in that disk to pile up and pop, and boom. And that's what you see. Yes?
This is, that chart said there was a radio jet that emits from that. Can you pick that up? Can we listen to it?
I'm not sure if they've actually observed that or if it's inferred. Is that the question?
Yeah, if it's observable.
Probably with... It depends on your instruments. In your backyard, no. With the big stuff, maybe.
So are you saying that it's exploding over and over again?
Yes. It never destroys the white dwarf. It consumes all the extra hydrogen in this titanic fusion explosion that makes it 100 times brighter, and then it's done. White dwarf's still there. It just starts piling up the stuff again. Over and over and over. Love that one. Here's stuff. I took these. These are a few of my picks, other than the one in my hand. I caught it bright, and then as you can see, this is a fun one too because it's got handy reference stars. If you look, these are my pointers here. Look, it's just as bright as that guy almost. And by here, it's only a little bit brighter than this one. And a few days later, it's barely brighter than that last one. So it's fun to watch, and it's particularly fun on the other end, where it's faint, and then the very next night, holy jeez, it's bright. It's pretty exciting when you finally see it. Here's my crappy GIF. People don't think stars can change. They do, and quite rapidly and quite violently. Okay, so we're going to run through the famous ones real quick. These are the naked eye ones, away from the telescope stuff. This one's up right now. It's Myra. It's a giant. It's one of the first knowns. It was known from antiquity, called this one was discovered in 1662. They gave it that name. It changes 1,500 times in brightness. At its peak, Very easy to see. One of the brighter stars in the sky. Second's pretty good. But it takes, a year and 2 months to go through the full cycle from bright to faint. Then we have Algol. This guy is one of the intrinsic ones. It's swelling in size. Algol is one of the eclipsing variety. And this is when the big faint one goes in front of the bright one. And then it's the brightest when you can see the two stars at once. And then when the bright one goes in front of the big faint one, it blocks out a little bit of the faint one, but it doesn't matter so much, so you get a smaller dip. It's in the fall, winter, spring. It's up pretty high in the polar latitudes, so you can see it for a long time. It varies with a slightly less than 3-day period. It changes brightness by 3 times. It's always naked eye visible. And this, if you get even a basic sky map will allow you to find it because it's a fairly bright star, medium. It is not tricky. That one has been known about for a long, long time. A lot of people didn't like it. They called it the demon star because the heavens were perfect and nothing was supposed to change. 7.5 million years ago, it was only 10 light years from us, and it was the brightest star in the sky, way brighter than Sirius at minus 2.5. And this is what's going on there. There's one eclipse. There's the little dip, and there's the big dip. Because the little one is much more contribution to the pair than the faint red one is. And of course, its total brightness is the highest when you can see them both. And some very clever bunch of guys got an actual picture of it at 92 light years out. But there it is. That is pretty spectacular. We got Beta Lyrae, Chiliac. This is a good one too. Vega's right overhead at night. It's super bright. It's practically the brightest thing you see when it's straight up. That's Vega. You find this little parallelogram and you want to look for that guy, Beta Lyrae. It's got a 13-day period, summer and fall. It's always naked eye. It's eclipsing. They're probably connected by a river of matter. It's one of these stars that are exchanging material. And so much so that the smaller member now was once the larger star. They're very tightly integrated with each other. And they may even have velocities in the system high enough that not all the matter gets captured by the star. And they believe from radio observations that it may have this crazy spiral going out from the system as they both lose mass. So, boy, that would be something to see. If I had that spaceship they fly around with in that Cosmos show, this is one of the things I would want to go see is this guy. Is this really going on? Plus, I'd want to be a safe distance from SS Cygni and watch it pop off once. That's got to be spectacular. So, there's all kinds of stuff you can see with your eyes. You got the lunar and the stellar motion, satellites, meteors. Whenever I go out, I check those last two because they're just there. And once you learn to find them, it's an easy thing to see. I've seen the one next to Vega go down a couple times. I've never, I don't know, Algol, it's been there forever. It's super easy to find. But I think what it is, it's the 13-day thing is throwing me off, and the eclipse is only a few hours. The Chiliac one lasts for about 12, so you can have a little broader window to see it. But it's fun to go out in one night, see with the naked eye that, oh, it is fainter. Look at that. Find a place without lights in your face. Do whatever you can. It's not that big a deal. Stay warm. Cold is the #1 reason people quit. I want to go inside. My feet are cold. Prepare for that. Overdress, and you will have an enjoyable time. You can take stuff off, but you can never warm up once you're cold. Nobody likes that. Get something comfortable. Don't be doing this, or you get astronomer's neck, and that'll bother you for a couple of days if you do a long spell, especially when it's cold out and your neck kinks up a little. I've kind of made a habit of this now. My yard is really dark. It's super peaceful in my place. I try to make a habit. If it's a nice night, I will go out and spend at least 15 or 20 minutes just chilling and watching things and thinking, talking on the phone, whatever. You really learn a lot about things just watching and spending some unwind time. And you'll start to recognize things, and those things will get to be your old friends, and you'll never forget them. No matter where you look, you'll go, oh, there's Delphinius. I remember that guy. And we got to have a little from last lecture, how it all turned out after all that build-up. We were out at the Bear Mountain up by Baker. There's my boy Jake. This is just before totality. We got all the stuff set up. That's what the camp looked like. Had a bunch of friends. This is us. These are some other guys. There's more people on the top. This road was just a freaking nightmare in the middle of nowhere. I couldn't believe it. Had a nice big hill, so we were flying our gliders off the top. Had a good day of that. The wind was perfect. No trees to run into or get stuck on, so that's always fun. And this is crappy screen grab from a 640 by 480 video. But this is right before totality. You can see the odd darkness of things. And then, of course, and then totality.
Good shots of the actual clips.
There. And the neat thing was, for solar min, somehow we lucked out and we got some spots to contrast with the eclipse going on. So that is freaking.
I didn't know what they were.
I heard that a lot. People kept cleaning their lenses.
Yeah. I realized after I looked it on my laptop that it was definitely something was there, and then I said what it was.
Uh-huh.
So, yeah.
And then a little bit closer, the last guy's about to go. And then, of course, totality, the exposure shifted so you can see the flares and prominences and stuff. And then there is the full corona. A lot of detail. God, that was beautiful.
That's a good corona.
Yeah, that was just amazing. So there's a lot of stuff going on. Thanks for watching. I hope you enjoyed it, learned some stuff. Give you an excuse to get out and look at the stars. Thanks.
Let you folks head out if you need to, but there still are a lot of people online.
Yeah.
So if you want to take questions from anyone.
Sure, I'll take questions. You
anyone
bet.
online, I think the speakers are on if there are any questions online.
Chris, how do humans, how do we track asteroids, the meteorites, like while they're in space? Once we found them, there's models, but before we find it, like the first time we identify it.
How do you tell where it's going?
Or how do we find it?
That's actually, it's fairly straightforward Newtonian mathematics, and it's been known for many hundreds of years. After Principia, they got this figured out within a couple of decades, and all you do is do observations over periods as short as a couple of nights, and from its path against the background stars, with them known and your time known and the Earth's motion known, you can calculate the orbit pretty rapidly.
How are they first identified? Because I imagine
as a moving dot.
Okay.
Yeah. You can see them on radars, but it takes sort of exceptional actions to do that, and you have to know where you're looking, like pointing a telescope at something with the radars, because of the return and all the radio frequency, all the RF implications of trying to bounce something off a moving object. The most common is a deep sky camera that's just taking pictures, and they compare them all to each other, and something is moving.
There's a project now,
That
right?
simple. What's that?
There's a project.
Oh,
now.
there's a ton of projects.
There's a bus-sized asteroid coming 27,000 miles.
Yeah, it's coming. No, I think it's like 9,000. It's coming well within
this month, right?
I think it is this month, and it's going lower than the geostationary satellites. It's getting in pretty close.
Any idea when?
I can't remember what day.
Possible.
Oh, it's all calculated. We know exactly where it's going. I was just reading this and not that.
Possible to capture though, as far as pictures?
Oh, definitely.
Okay.
Yeah, definitely. And this is one of those things where, of course, all this motion starts to play in. It's coming close and it's moving, so it's going to do its pass pretty rapidly. And if you're on the wrong side of the Earth and it's passing over here, well, you're out of luck.
Yeah.
And I don't remember if we're favored or not.
Okay.
But in terms of can it be done, yes, relatively simply. And if you don't want to try to get a picture of it where it's more than a dot, it's much easier to capture because you can pull back and get a wide field and see it trundling along. Your aim isn't as crucial. Yes?
Do you have any recommendations for resources or websites or something that have like pretty detailed list of events, like celestial events that are.
Space weather. Spaceweather.com is my go-to. It's a daily, spaceweather.com. It's a daily thing on what's going on. They have all this stuff, everything on this list. Comets, meteor showers, aurora, satellite launches, satellite pictures. This is where I got the map of the meteors, the orbitals. This is where you find that simulation of the aurora. Everything that's happening currently and you could do visually is on spaceweather.com. It's a great website.
Any other questions? Any questions online?
Yeah, will you guys post this video on YouTube like you did for the Lincoln video?
Yeah, I think so. Yeah, I'm gonna double check to make sure we can, but I think we'll be able to. Yeah.
That'd be great.
Not
Chris,
the
you've
link
become
regardless.
you're my homeschool science teacher, Chris. Thanks.
Well, thank you.
Yeah, I have a question. Can you hear me?
Yeah.
Yes.
We can hear you.
Okay. You showed they used to have one out there that's like a Google Earth with all the satellites that are around the Earth. Do you
Yes.
have a link for that? And the questions concerning that is, with all of that debris out there, both live and probably junk, can some of those be confused for meteors that, come down and because like the copper and everything must flash off green or blue or something, and the metals that are in those things. And just that mainly. And how do they negotiate around that stuff just to get back to where they need to go, like to the moon or something,
Well, this, of course, makes it look worse than it actually is. It's the same thing with airliners and civil aviation. It's the big sky theory. As long as you're not doing anything grossly wrong, everybody's going to be okay. And then you amplify it by the volume that there is around the Earth. Because, of course, this is sort of deceptive as a projection of a three-dimensional volume onto two dimensions. And so stuff looks close that's actually on opposite sides of the ball. And so it's just not quite that crowded. That said, there's a lot of concerns about it because it's getting crowded, and particularly debris from placing satellites in orbit. Because when stages deploy, pieces of paint flake off, bolts flake off, all sorts of stuff comes out. And as you know, at these speeds, even a flake of paint is deadly. I can't remember when it was, but they had the satellite collision. It was like 10 years ago, and this huge cloud of debris came from that. And they were very concerned. Now they have to track this cloud of crap that's slowly expanding as it matures.
Yeah, and the Chinese blew one up, and then we did too, just to show we could.
Yeah.
Remember, right?
It's really bad, really stupid. So now, as for do we see it as meteors? Not so much. It does happen. I've seen a couple of pieces. Space weather will tell if they're going to deorbit a big one and where you can look. So that's fun. The colors are, as a matter of fact, different, as you point out. Not so much the copper, but they tend to be very orange and fiery looking. I can't really describe it all that well, but it's not this nice, tightly constrained thing that when you see a momentary shooting star, partly because the velocities are so much lower, you get a good long look at something deorbiting. Stuff intersecting the Earth is traveling, on the whole, much, much faster. And, the longest meteor you've ever seen lasts, 3 or 4 seconds? But you'll watch something come out of low Earth orbit, and it'll take a minute or two to cross, because think of how long satellites take to cross the sky. It's moving the same speed. And so that's the chief determinant. If it's unusually slow, but it is burning, it's likely a piece of of human stuff.
Thank you. And where do we get a live look like that of all the debris out there, the space satellites and whatnot?
I don't understand.
Right behind you, you have the mapping of all the satellites, and used to be able to look at it, click on it, and you see the names sometimes pop up if they're not classified. I lost your sound.
With that, I think the mute button got accidentally hit.
So
Okay.
we're back now.
Yeah.
Okay. So yeah, just Google around for live satellite tracker, and I think
Okay.
you might even be able to get there from space weather. And it's exactly like you described. It's got all this, and you click on any dot, and it'll show you the orbit and the satellite and all that good stuff.
Thank you.
Yeah, you bet.
Any other questions online? All right. Well, thanks, Chris.
Okay. Well, thank you. It's been a pleasure.
Presentation.
Great job.